Hello, this is Jonathan Templin, and this is a lecture about mathematical statistics, univariate distributions, including the normal distribution, and how linear models work with the normal distribution. This is online lecture number 4 of our Fundamentals of Multivariate Modeling course, which is EPSY 905. In today's class, we're going to cover the building blocks of what underlies the statistics that we use in class. We're going to start with random variables. These are the types of distributions that are out there, the types of variables can take. And the main reason for this is because not all the time are you going to have variables that fit the assumptions of the linear model. For instance, you may have some type of binary variable. You know the linear model has a conditional normal assumption, but there's no way a binary variable can ever meet that assumption. So what do? The answer lies in changing the distribution of the variable. We will cover a few of the univariate distributions to get a feel for what these are, talk about the general terminology of where these fall into, and describe the univariate normal or Gaussian distribution, and a couple other continuous univariate distributions, so we sort of get a feel for the different distributions that are out there. We'll also cover the types of distributions that we often encounter in statistics, including marginal, conditional, and joint distributions. Joint distributions being multivariate, which gets us prepared for the multivariate section of the course. Marginal being univariate, or marginalizing across some other variables, and conditional being something like you talk about with a linear regression. We'll also get into expected values, means, variances, but more importantly, the algebra of expectations. This is the part that underlies why, for instance, the GLHT function has to be used to figure out the standard error of linear combination of your betas in a linear model. So that's where we're going. Then we'll finally put it all together and talk about how the linear model fits within statistics, show how it works with the normal or Gaussian distribution, and talk about how we might want to assess the assumption that the error terms are normally distributed. So we'll dive right in with random variables and statistical distributions. Let's go with the definition. A random variable is made up of two words, random and variable. Random is defined as a situation in which the certainty of the outcome is unknown and is at least in part due to chance. And a variable is a value that may change given the scope of a problem or set of operations. So you put that together and you get a variable whose outcome depends on chance. And these possible values might represent the possible outcomes of a yet to be performed experiment. So today we're going to denote a random variable with lowercase x. That thing is going to be random. Now often there are different types of random variables that we differentiate across. Random variables may be continuous, for instance. So in this case you might have the height of a person from a class drawn at random, or you might have an outcome in a linear model. Something that has a continuous random variable has numbers that can take pretty much any value, and by value I mean certain decimal places. They're not entirely discrete or categorical. So height in inches is a good example because we can have all sorts of numbers of heights depending on how precise our measurement, our ruler or our measuring stick happens to be, because we may have someone who's 72.01 inches or so. Right? So you can think of this continuous variable of height. Variables also may be discrete, also called categorical. And an example of a discrete random variable is the gender of a person, or the sex of a person. So if you take a person at random and you want to assess, you collect what sex they happen to be, you have a set of very discrete finite points for that. Then you also run into random variables that can be a mixture of continuous and discrete. So for instance, x might represent the response time a person takes to answer a question, so long as it's between 0 and 45 seconds. But after 45 seconds, the question asked may just move on, and so at that point we just put a 0 down for x. So it's either categorical in that it goes beyond 45, they didn't answer, which effectively is 0, or we can provide a value to it, doesn't really make a difference how we do it, or it's an actual quantitative time that goes between 0 and 45, not including 0 itself. So there's some key features of random variables. Each type of random variable is described by something called a probability density or probability mass function. Often we refer that as a PDF, probability density function. So, and we may just denote it generically in mathematical terms, that the function of the random variable indicates how likely it is to occur. More specifically, that really talks about, what I'm talking about is a type of curve. And so you can think of the normal distribution. You've seen the bell curve before. That is a type of probability density function. And any one spot on that curve indicates the relative frequency of occurrence of an outcome. Right? And so it's a mathematical function that gives us a rough picture of the distribution from which this random variable is drawn. There are all sorts of PDFs, all sorts of distributions out there. In fact, you can create distributions for any type of variable that don't really fit a given form. But typically in statistics, you work with distributions that have very specific forms. But overall, these types of the type of random variable, discrete, categorical, continuous, and so forth, dictates the name and nature of these functions. So, for instance, if we have a continuous random variable here, then f of x, its PDF, is actually called a probability density function. This is where we say PDF. And this PDF, this probability density function, you can think of the normal distribution as one of them. The area, if we were to quantify the area under the curve has to be equal to 1. And we do this often is by calculus. We integrate over the set of the curve. The height of the curve, so for any given value, that height, like here, so if we have a value x right here, where it is on the curve represents the function value, right? So we plug in x into this f of x deal, and it returns the height of the function. That can be any positive number, right? So it doesn't have to be somewhere between 0 and 1. It's not a probability. What it happens to be is a relative likelihood, a relative frequency, in that a value of x that's right here has a height right there. But if we have another value, let's call this x prime or something like that, its height or its likelihood is right there. We can see that x prime is a more likely number because it's part of the curve, or its height on the curve is higher than x. So that's how this works. The numbers themselves don't typically have meaning without a relative sense. So that's a key thing in a continuous random variables probability density function, or PDF. Now, in discrete random variables, f of x is often called a probability mass function. So you can think about this. If, for instance, let's say we have two types of people. We have people who've graduated from high school, so we'll call this H as high school graduates. And we may have non-graduates over here. And what this probability mass function looks like is the portion or probability a person happens to be a high school graduate versus not. Now, that's a terrible drawing right there. We have a lot of non-graduates, but, you know, it is what it is. This right here would be the probability, the x of x, or the probability, or what we actually call the f of x. Now, the height of this thing is also a likelihood, but because it's discrete, we can actually call this a probability. So that's often where the term probability mass function gets used. Now, in general, I'm just going to call both of these PDFs because it's just easier to denote. But the key difference between a continuous random variable and a discrete random variable is in the discrete random variable, we can interpret the number that comes out of the function as a probability because there's a discrete set of categories we're talking about. Whereas in a continuous random variable, the number that comes out of the function cannot be interpreted as a probability, but it is more like a relative frequency. You'll also note that this sum of the heights of these bars must equal 1 in the discrete random variables case. That is, again, that's how to make a distribution. The reason for that is we wanted to be able to talk about kind of the overall proportion of things happening, and everything has to be effectively exhaustive over the sample space. So we have to think about there can either be two types of people, high school graduates or non-high school graduates, right? We have to divide up the types of classes of people there are so that it exhausts the space of outcomes that could happen so that we can talk about the entire set of probability itself. And again, because the height of the bar, or the height that or the value that comes out of f of x is a probability, they have to range from 0 to 1. Whereas in the continuous case, you can have distributions with heights well above 1, depending on how peaked the distribution happens to be. So there are other key terms that we have to pay attention to when we talk about distributions. One is the sample space. The sample space is the set of all values that a random variable x can take. Right? So for instance, the sample space for a random variable x for a normal distribution is between negative infinity and positive infinity. It's all real numbers. Now, I will note that we use a normal distribution almost for everything, even if we know that our numbers don't necessarily go all the way to negative infinity or positive infinity. In case in point, an example would be if we're trying to predict somebody's weight using a linear model. Effectively, though, with a normal distribution, we know that there's a certain number of, we know the mass or the big chunk of the bell curve sort of in the middle. So if I draw it here, right? So in the middle part right here is where the most of the bulk of the proportion of the distribution happens to be. And as you get further up to infinity, or further below down to negative infinity, it functionally gives you a value that's so infinitesimally small that it's hard to quantify. And that's usually why the normal distribution works so well for data, because in the ends, it can easily shut off kind of the high point or the low point, so that the value that comes out of the distribution function, kind of the height of the curve, is so tiny that it doesn't make much of an impact. So that's the normal distribution. Again, any real number. We also call this the real number line, right? The sample space for a random variable x representing the outcome of a coin. So we flip a coin. The coin flip can either be heads or tails, right? So that's a different type of sample space. It's a discrete random variable, and heads and tails are the two outcomes. I guess technically you could land the coin right on its edge, but let's imagine that's impossible. We've made it so that doesn't happen. Also think about if we have a six-sided die. If we rolled that die, the sample space of outcomes would be 1 through 6, the number of dots that are facing up. So the key, and why we're talking about sample space, is eventually when you start to think about the different types of models that exist for your data, you have to pick a sample space that matches with the range of values obtainable by the data themselves. And so this is sort of the key. The dance is, how do I figure out which distribution to use for my data? I know perhaps conditional normality may not hold. What do I do? The first step to think about is what's the shape of the distribution? What is the sample space of the distribution? And where are the most likely values to be? That helps govern the choice of a distribution family to use in a type of model that we'll talk about in the generalized linear models section of this course. So, statistical models. Why we're talking about this is because statistical models make distributional assumptions on various parameters of the model or on the data themselves. And these assumptions are critically important. They govern how we estimate the models. They govern how we make inferences about the results. They also talk about how we may have missing data and how we might resolve a missing data issue by imputation or other means. So you would imagine if they're critically important in the process of understanding models and getting estimates from model, then you should realize, or you probably imagine, that if the data don't follow the type of distribution you're looking for, or that you assume, that you may get inferences that may be inaccurate. And so here's a big throwaway statement. Sometimes that's a problem, and other times, not so much. What do I mean by that? There's some pretty clear-cut cases where there is a mismatch between a type of model and a type of distribution. For instance, if we use our typical linear model, right, our conditionally normal linear model, the thing we'd see in regression or ANOVA, but our outcomes are only have a couple categories, a binary or maybe 3 categories themselves. That's usually a very big problem. That normal distribution is great when you have, a nice cluster of continuous data. When you get away from that cluster of continuous data, you tend to have problems in that it tries to map in between. It doesn't work very well. That's a big problem. Where it's not typically a problem is if we have continuous data and our residuals aren't exactly normal. Maybe we have a few of them that are above or below kind of a limit where we'd like to have. that doesn't typically impact our results too much. So it's sort of a balancing act, and practice really governs where the limits of this happen to be. So it's really important then to check your distributional assumptions while you're running statistical analysis. Now I would say prior, but again, we don't want to go and take data, for instance, prior to running your analyses is a little bit more difficult. Like you think the linear model sense, I said before in one of our previous lectures that we don't make any assumptions about X, our predictors. But yet you still see people trying to quote unquote normalize them, or even Y. We don't make the normality assumption about Y or marginal normality about Y. We say it's conditionally normal. You still see people trying to make it normal before they put it into analysis. That is a big no-no. Don't do that. What is more appropriate is to look at the range of the data, right? Take a look at the data, see the range, and see if that range plausibly matches up with the model you're trying to use. If it does, that's great. If it doesn't, and again, this is the big picture category. You've got two categories, and you're trying to think about using a normal distribution or conditionally normal distribution. That's where you switch the model. But overall, the model runs first. Most often, we run the model first, and then we go and take a look at the results and start taking a look at the assumptions. So let's dive into continuous univariate distributions. So just to see a little bit more about how these work, we're going to discuss three of them. We're going to start with a uniform distribution, which we hardly ever use in the analysis world. Like it's never a distribution that we use for data, most likely. However, it is a very frequently used distribution in Bayesian statistics as a prior distribution. It's also very, very frequently used in Monte Carlo simulation studies. It's how we draw our parameters at random when we simulate data. Then we'll move on to the normal distribution. Everybody loves the normal distribution. That's why it gets the name normal, sort of a misnomer. If you get into different types of statistics texts or in different parts of the fields of statistics, you quit seeing the word normal as much, and we often call this Gaussian, G-A-U-S-S-I-A-N. Named for Gauss, I'm forgetting his first name, was the person who really started using or discovering that distribution. And just to sort of wrap this up, we'll have a ChiSquare distribution, which you've heard of ChiSquare before, but sure enough, it has a distribution. We can talk about its shape and its parameters. So about the distributions, each of these are continuous, and so f of x for those will be a probability density function. It will be some type of curve or line where if we plug in a value x, we get a result that talks about the relative likelihood x occurs. But how the function works, rather than just plug x in, get number out, is usually through a set of parameters. Each distribution has a set of parameters. And often those parameters are what we're going to take advantage of to use in our data analysis. For instance, when we get to the end of this lecture, you're going to see in the linear model, what we're doing with the fixed effects, with the beta weights, is we're trying to provide a parameterization for the mean of the distribution. So we substitute out the mean with this kind of regression line, which provides a conditional mean for what we're doing. So often what we do is put constraints on these parameters, such as the regression line or some other type of imposition, and those constraints are based on the hypothesized effects in the data. So we'll see that at the very end of this lecture, that if we have this hypothesis that the mean of a distribution varies as a function of x, then that is the constraint we're putting on the mean itself to go about getting what we're interested in our information. So let's just talk about the uniform distribution. The uniform distribution is called uniform because its distribution shape is a flat line. Really, really interesting. Not quite. The random variable itself ranges between A and B, so A being the lower point and B being the upper point, the minimum and the maximum. And the distribution function, because again, this distribution function has to, the area under this curve, right under here, has to be equal to 1. So therefore, the height of this function is b minus a. And if you kind of think of this as a box, we could always find area with length times width. What you'll find is that this distance is b minus a right here, and this height is 1 over b minus A. And so if we multiply B minus A times 1 over B minus A, we get an area in here of 1. So that's why this distribution function shows up. So why am I mentioning this? How it works is this. If you have a value somewhere between A and B, let's say right here, and you plug that into this function, the result you get is 1 over B minus A. If you have another value over here, plug it into the function, the height you get is 1 over B minus A. So long as the values you're plugging into the function are between A and B, they will always return the same likelihood, the same relative likelihood. And this is why the word uniform gets used with this distribution, because everything is uniformly likely to happen within this range from A to B. So often we denote this with the following notation down here. X, this thing, this tilde means is distributed as uniform between the range A and B. So again, just to show how this works, we're going to try a few values here. Here, if I plug up, if we know the range is between A and B, right here with these first two lines, a 0.5 gives us a 1. Sorry, A and B is 0 to 1. Pardon me about that. 0.5 gives us a 1. 0.75 gives us a 1. So we'd say they're both equally likely to occur. And that's why the uniform happens. If we have a range from 0 to 20, you'd see that the distribution function is 1 over 20 minus 0. So we put a value of 15 in and we get a 0.05. Similarly, if our range was 10 to 20, we see our PDF height is 0.1. So a value of 15 gives a 0.1 likelihood. Now note, you'd be tempted to say that this value is more likely of occurring than this value. But remember, because they have different sets of parameters, it's not the same. It's like comparing apples to oranges here. So we wouldn't be able to say that that is the case once we start changing those numbers. So because everything's equally likely, you don't see the value of x in that PDF function, right? The PDF is 1 over B minus A. The mean of this distribution we can find is right at 1/2 A plus B, and the variance is 1/12 B minus A squared. And I think this is funny. Why 12? What? Well, there'd be a part of what our lecture as we go forward will tell you is why, but that's sort of trivial and not really needed for what we're doing. It's just funny to see a number like 12 show up, or 6. Okay, let's get into normal distribution. So again, if you have an x that ranges somewhere between negative infinity and positive infinity, and again, sometimes we denote this as the real number line, which is like 2 lines and an r on top of it. The univariate normal distribution is provided by this distribution function here, which is really ugly. But like I remember the first time I saw it, I'm like, oh, I don't want to deal with that. But no, really, it's actually, once you start getting into it, you start to see the beauty of it. You just have to give it a chance. It grows on you. It's got a great personality. This distribution is characterized by 2 parameters, the mean, which is right here, and the variance, which shows up right here and right here. So let's just kind of walk through this. 1 over the square root of 2 pi sigma squared is on the outside. We call this sometimes the normalizing constant. And in the exponent, this exp is Euler's number, or e, where if we took e to the first power, it's approximately, wiggly equals, 2.71. This is x minus its mean squared over 2 sigma squared, and that whole quantity times -1. That's how it works in the exponent. Mu and sigma squared are, if we have the sample values for them, they're called sufficient statistics, in that they can, if you have a random variable x that is truly normal, you can characterize all of its distribution using these 2 numbers, the mean and the variance. You'll also note that there is the skewness and kurtosis. There are no parameters for those. They're fixed. In fact, there is no skewness, and kurtosis is set to a constant value that we don't really need to talk about. So our typical notation is this. X is distributed as normal with a mean of x, mu x, and a variance of sigma squared x. And the nice thing about normal distributions, the thing that we're going to use in the result later on in this lecture, is that linear combinations of random variables right? This is the adding or subtracting numbers, weighted numbers of random variables. So if all the random variables follow normal distributions, then the result of this linear combination, the thing that comes out of it, is also normally distributed. And this is why we use the GLHT function when we get into linear models. We're going to uncover that shortly. So here's a nice plot from Wikipedia of normal distributions. F of x, that crazy, ugly distribution function, gives you the height of the curve. All right, so take a look at the blue line. The height, the peak, the maximum of that function is given at mu, right? So here, the blue line, the mu is at 0, mean is at 0, so the peak of that function, right, is at 0. The variance governs how wide the distribution happens to be. So this is the blue line is the distribution with a variance of 0.2, whereas if we go down, again, the red line now, this has the same mean but a wider variance. So again, if we wanted to go and talk about the relative frequency with which observations occur, let's imagine an observation that's right here at 0.5 versus an observation that's right here at 0. Going to the blue line, the 0.5 observation, that is f of x. This is f of 0.5. And this part right here is f of 0. So if you were to talk about which observation was more likely under this distribution, you could compare the two, and really the one that has the taller or the bigger number that comes out, in this case f of 0, is more likely to occur in this distribution. And finally, you can see the other lines here, like the yellow line is where you have the same mean of 0, but now a much wider variance. And then, of course, you have a different mean. The mean shifts over here. So you can see the different curves for each of these. So to demonstrate how this normal distribution works, we're going to try a few values, right? Let's imagine in the top two, right here, the mean of 0 or variance of 1. Sometimes we call this a standard normal distribution. If we try a value of 0.5 versus a value of 0.75, we plug it into that ugly function from 2 slides ago. We see the f of x, the result, is 3.52 for 0.5. That's the height of the curve. And 3.01 for 0.75. And actually, if we go over here, you'll see kind of the difference. There's f of 0.5. This is f of 0.75 right there. So you'll see f of 0.5 is more likely relative than f of 0.75, right, or 0.75 under the standard normal distribution. And again, we can plug in other values for x with different means. And again, we get the different heights. Similarly, here's the last two, mean of -2, variance of 1. If we're going to compare a 0.75 with a -2, you'll see that -2 being right at the mean is actually going to be much more relatively likely to occur than the 0.75 value. Now these numbers that I found over here, I found using Excel. If you go into any of the cells of Excel and type equals norm dist, it'll pop up a little box asking for a value and the mean, the standard deviation or variance, and it'll give you back the value, the number itself. Similarly, in R, you can use the dnorm function to do this. All right, one last continuous distribution is the chi-square distribution. This is often used in statistics because it's often a reference distribution for a lot of our statistical parameters. We're going to see this almost all the time when we get to maximum likelihood. Again, the sample space for variables that actually this is likelihood ratios follow this distribution, or also if you're generating data, the actual sampling distribution of the variance follows a scaled chi-square. It's a chi-square that's been modified by a constant. For a continuous random variable x that ranges from the sample space goes from 0 to infinity, and that does not include 0. It's just above 0 to infinity. The chi-square distribution is given by this ugly function. So not only is this an ugly function, within it there's another ugly function called the gamma function. It's terrible. I don't need you to remember this because we have lots of software that will remember this for us. We don't need to do this. But what I do want you to understand is that, again, just like the normal distribution with the mean and variance, and just like the uniform with the minimum maximum, the chi-square distribution has a parameter. It looks like a V, but we call this the Greek letter nu. And it's referred to often as it's one distributional parameter. In many cases, it's called the degrees of freedom. So if you remember using chi-squares in statistics before, you'd see a degrees of freedom underneath the chi-square kind of in a subscript, and that's really the one parameter of the distribution that involves. In this distribution, the mean of the chi-square is equal to the degrees of freedom, or nu. The variance is equal to 2 times that value, 2 times that parameter, 2 times nu. They're always fixed. That's always what they happen to be. The other thing that's interesting about a chi-square is that if you're used to degrees of freedom, you're used to a value that where we usually have integers, like 1 or 2 or 3 degrees of freedom, or however many you want to have. But actually, there's no expectation that nu is an integer value. So think of it this way. The chi-square is a continuous distribution that ranges from 0 to infinity. And because of that, the mean of that can be also following that same sample space. Right? It can be between 0 and infinity. And if we know the mean is nu, we know that we can have non-integer degrees of freedom, or non-integer nu parameters that go into the model. And sure enough, when we get into mixed models in this class, we're going to start to see chi-squares with non-integer degrees of freedom. And that is because oftentimes when we have multivariate data, we may have some type of dependency or correlation amongst the outcomes. That correlation effectively brings down the overall sample size we might have, but it brings it down in not in an integer fashion. It's sort of a non-integer fashion, and so oftentimes we'll start to approximate distributions using some type of non-integer degrees of freedom, which looks crazy if you're used to the integer degrees of freedom, but it's completely legitimate. Here's the shape of the chi-square distribution. What you're going to see is as nu is 1, it's got this crazy decreasing function here. But as nu starts to get bigger and bigger, remember this is the mean of the distribution, right? So the mean of this is at 1 for the black line. The distribution starts to have its peak move away from 0, right? So here the pink line has a mean of 5, and again, the chi-square is often when the value of nu is close to 0. This is a skewed distribution, right? This distribution has most of its mass on the left side, but it's positively skewed as you go forwards. The mean gets pulled out by that tail on the right side. But as the degrees of freedom gets more and more and more, this distribution moves off 0. It starts to look a little bit more like a normal distribution as you get further out away from 0. Okay, those are some examples of continuous distributions. Let's talk a little bit about marginal, joint, and conditional distributions. These are an important topic because understanding what you're talking about, characterizing result, typically falls under, we do it a little bit different when we talk about marginal, joint, and conditional. So let me go a little bit further here. Let's imagine we go from one random variable to multiple ones. So let's imagine we have 2 discrete random variables. Basically, we're going to have x being the outcome of a coin flip of a penny. It could be heads for the penny or tails for the penny. And z will be the outcome of the coin flip for the dime. It could be heads or tails as well. And the 3 types of distributions we're talking about, the marginal distribution is going to talk about the distribution of x regardless of what happens with z, or the distribution of z regardless of what happens with x. The joint distribution talks about both x and z together, so if you flip them both at the same time, this is the multivariate distribution. And a conditional distribution is the distribution of x given z. So I know that z turned out to be a heads. What's more likely, heads or tails on x? Or vice versa, the distribution of z given x, actually. X given z, z given x. My example there was z given x. So, marginal distributions. We have pretty much worked with these exclusively in this lecture up to this point, and they represent the distribution of typically one variable by itself. Right? So, univariate distributions. We could be talking about the flip of a penny versus the flip of a dime. Where marginal distributions start to show up, what I'm thinking about is when people start to use the normal distribution or when people understand the assumptions of a linear model to say that the outcome variable has to be normally distributed. And I keep saying that's incorrect. The mistake they're making is they're thinking that the marginal distribution of y, regardless of what x happens to be, has to be normally distributed. And that's the big mistake. It's not the marginal distribution of y, it's the conditional distribution of y. It's y given the value of x, and that's a big difference between the two. And the difference is literally in the marginal distribution of y, you're saying, I don't care what x is, I just want y to be normal. There are a few statistics where you have to have that, but linear regression, ANOVA, linear models in general do not have that distinction. Joint distributions. So we go to joint distributions now. This is our first shot at a multivariate distribution. This is essentially two variables at once. So what is the likelihood of a heads and a heads showing up, or heads and the tails, or any different combination themselves? Often we take joint distributions. We're going to use these to introduce two topics, independent variables. So if this is a penny and a dime, I'm assuming these to be independent. If you just pull these out of your pocket and flip them, you see them to be independent. What do we do with independent random variables? How do we form the joint distribution? But generally speaking, when we get to maximum likelihood estimation, when we get to Bayesian statistics, how we form our likelihood functions comes from these joint distributions. They're critically, they show up everywhere. So if we have a joint distribution of independent random variables, it's actually quite easy. Let's imagine the penny and the dime just come right out of my pocket, and I can flip both. Here, I can form a contingency table. These are discrete distributions, right? So let's imagine I have a dime and a penny, and this is heads, and this is tails, and again heads and tails. The bulk of the numbers that show up, the probability each one of these four outcomes, right, heads on both, tails on both, or kind of a mix, occur, is the joint distribution. That's the joint distribution of the penny and the dime together. The nice thing about this is if you have a penny and dime that comes straight out of your pocket, they're likely to be, or they're actually going to be independent, almost certainly going to be independent, meaning that you can describe this joint distribution solely by the product of the marginals. And think about it this way. Say, let's take that, if these are independent, there's a 50% chance I flip a head on a penny. So, and actually you can see that right over here. That's the marginal distribution of a penny right here. That's the 0.5. And let's imagine then, okay, great, I flip the penny, it turns out to be a head. Now there's a 50-50 chance I flip a head on the dime, which is right here. So let's call that 0.5. If these two marginal random variables are independent of each other, then the joint distribution comes from the product of the marginal values. And so if we want to talk about the probability that we get heads on both, we multiply them together. 0.5 times 0.5 gives us a 0.25 up in this cell. And as it turns out, if these truly are independent, you'll see 0.25 on each of these, because each of the margins tend to be are at 0.5, and there's 0.5 here and 0.5 here. So this contingency table actually summarizes the joint distribution in the middle, and on each of the sides, or in each of the margins, it's the marginal distribution, right? The marginal distribution of the penny, marginal distribution of the dime. Again, because these are discrete random variables, these are probability mass functions. These are actual probabilities that show up in this table. So there we go with numbers. So how we marginalize across a joint distribution, though, how do we get from these numbers right here, 0.25 and 0.25, to this number on the side? Well, it turns out, just like you would know in a basic statistics class, we take the sum in a discrete distribution. Take 0.2. So for each row of this table, we take the sum of the cells and we get the margin. For each column of the table, we take the sum of the cells and we get the margin. And so that's what this is saying right here. The sum, the marginal distribution of the likelihood of a penny, or the distribution of the penny flip, comes from the sum of the joint distribution across the values of the dime. So in this case, the likelihood a penny is heads comes from the sum of a penny being heads conditional on dime being heads, and the sum of a penny being heads conditional on dime being tails. For continuous distribution, that's where we get this integration term, and nobody wants to talk about that. But no, really what happens is that this the integral itself acts like an eraser. So it effectively says, I'm going to go and take the integral is a very complicated sum, you can think of it as. So basically doing the same thing. If I want to get the distribution of x, I need to erase the distribution of z, so I put it in this integration function. But we don't need to know calculus for this class, so it's okay. So a conditional distribution, then, is a distribution of one or more random variables conditional on the value of another random variable, one or more random variable. We say this is the distribution of z given x. And how we find that is through a division process. The distribution of z given x is given by the joint distribution of x and z, OINT, divided by the marginal distribution of x. And we find these conditional distributions everywhere. In fact, where Bayes' theorem comes from is this same process. It's sort of one half of the step that we get to when we talk about Bayes' theorem when we get into Bayesian statistics. But moreover, more specific to what you've learned so far, the general linear model uses this conditional distribution, right? Where it's really what we're talking about is the distribution of y, our dependent variable, given x, our predictors. So here's another example for that same contingency table. We have our joint distribution in the middle. We have our conditional distributions, our marginal distributions on the side. If we wanted the distribution of z given x, we take the joint. So let's imagine the heads part of z, right? So we go right here. What's the probability z is heads conditional on x being heads? Right? So we take the 0.25 that shows up right here and divide it by the probability of the penny being heads themselves, giving us a 0.5. Same thing that is if we want the distribution of z being a tail, right here, conditional on x being heads, it's the same value. And what you'll note is this 0.5 value for both is really just an indicator that the two coins are independent. Okay, moving on. We're going to talk about expected values and algebra of expectations. This is really where we're going to get into why GLHT works. Expected values are means, put another way. But they are statistics that we look at. They're sort of a theoretical mean. If we take a look at a sample space of a random variable, and if we provide a weight to each value of that random variable, then the expected value is the weighted sum or the weighted integration of that random variable. That is the term, weighted integration. The weights themselves correspond to probabilities or densities, depending on the type of random variable you're talking about. And the typical notation we use is this capital E, and in brackets we put x. And so here, this is kind of the expectation function. The actual statistic that's being weighted is being put into parentheses where x is. So let's talk about, so why do we use this? We use this because we want to understand what the general linear model is telling us about our data. So for instance, what is the expected mean roll on a six-sided die? Well, what we have to do is figure out each of the outcomes. Well, there's a 1, a 2, a 3, a 4, and a 5, and a 6. So that's the number that you can get when rolling the die. We have to weight that by the probability that outcome occurs. So 1/6, let's call it a fair die. So we take this weighted sum, and we see that the mean of that die is 3.5. And again, for continuous variables, we replace the sum with the integral, but nobody wants to do that. But sure enough, the expected value itself, this is a fairly straightforward idea. It's sort of a weighted sum based on how likely events are to occur. The variance turns out to be another type of expectation, and so does the covariance. So often you see this variance function. It turns out the variance is the expectation of a random variable minus its mean squared, right, which is often denoted with a mu for x. And that this formula is going to help us understand the predictions we make with the general linear model and how it corresponds to the statistical parameters that we interpret. So for instance, if we wanted to talk about how much variance there was expected in the theoretical die roll, we do the same process, right? we know that the values of the die roll can be 1, 2, 3, 4, 5, and 6. And we also know that they occur with probability 1/6 for each of them. So we put the values into this function, and we subtract off the mean we found a few slides ago. We sum them all together, and we get 2.92 as a variance. So likewise, the standard deviation, expected standard deviation, is 1.71. And sure enough, if you have a fair die and you roll it, hundreds of thousands of times, you're going to find the standard deviation is 1.71. A good way of interpreting that is to say the average roll of the die is about 1.71 points off of the mean, or 1.71 away from a 3.5. Likewise, if we have a pair of random variables, we could do the same thing with covariance, although I'm not going to go too much into that. But right here, the covariance between x and z is really a set of expectations, the expected value of the product of x and z minus the expectation of the product of the means of x and z. But why I told you that story was to tell you this one. We're getting into linear combinations of random variables. Sure enough, expectations have ramifications for what happens with those. And again, a linear combination is a weighted sum for a random variable, right? So if we take a bunch of weights, a1 through an, we have a set of random variables, nu 1 through nu n. We can sum them together and get x. This looks like a linear regression almost. So we're going to use the algebra of expectations to talk about how things change when we change values. So for instance, let's go back to the height-weight data set that we had seen earlier in the class. This is a sample of people. We took half of them are male, half of them are female, and we have heights in inches and weights in pounds that came about. We also have a covariance matrix up here above the diagonal and correlation below the diagonal. So what happens, this is sort of telling us why the distributions change when we do things to the data themselves. If we have a random variable x and we add a constant to it, then the expectation of x shifts by that constant. What does that mean? It means we're just shifting the mean by adding a variable to it. I think that tends to make sense. The other thing of note is that when we add a constant to that random variable x, the variance stays the same. We're not expanding or shrinking the shape or the mass of the distribution. We're just moving its center. Similarly, the covariance, if we had two variables, x and z, and we added a constant to one of them, the covariance is unchanged as well. We're going to see this with numbers in just a moment. Now, what happens when we multiply the random variables by a constant? If we take a random variable x and multiply it by a constant c, and we take the mean and multiply it by that constant. Same thing with the variance. Multiply the variance by c, multiply x by c, but the variance of x changes by that constant squared. And really, this is, if we're talking about standard deviation of x, it would really be the constant itself, because remember, the variance is the square of the standard deviation. And similarly, the covariance changes as well when we have a c and a d times this covariance. And finally, when we put it all together, the sums of random variables, if we have cx plus dz, we see that it shifts both the means by c. And here's the important part, why we have to use the GLHT function, is that if we had c times x plus d times z, the variance of this thing, of this new random variable, comes from c squared times x, that's this result right up here, plus d squared times z, which is right here. But now we have a covariance term we have to worry about, which is 2 times the constant, the multiplying x, times the constant multiplying z. But in theory, that sounds fine, but let's get into numbers. Imagine you wanted to convert weight from pounds to kilograms, where 1 pound equals 0.453 kilograms, right? So the new random variable weight would be 0.453 times weight in pounds. So what would happen to the mean for this? Well, again, the mean would change by 0.453 times the original weight of our data, giving us 83.08 kilograms. What happens to the variance? Variance shifts by that constant squared, giving us a new variance of 652.38 kilograms. And similarly, what would happen to the covariance between height and weight? Well, sure enough, we'd have to take 0.453 and multiply it by original covariance, giving us a new covariance of 151.68 kilogram inches, which is, again, covariance is weird. We don't talk about it very often. But don't take my word for it. Here's where I did it in R. Here's my new variable, weight kilogram, right here. And I'm going to describe the variance here. The weight in kilograms, mean of it's 83.08. Don't have the variance up there, but if we chose the covariance matrix of weight kilograms, here's the covariance of weight or the variance of weight kilograms. And so you'll see the covariance of it with pounds is 151, or height in inches, 151.6787. But similarly, you'll note that the correlation is unchanged, right? Because correlation doesn't have scale or doesn't have units. So if we were to look at that, it doesn't change. And furthermore, with this linear combination, the new variable, weight in kilograms, is correlated 100%, or correlation of 1 with the previous random variable. So where are we going to use this? Turns out that GLHT function, the thing that shows up all the time from the multcomp package, is why we use this. So what we use the GLHT function for is a linear combination of the betas, or the original model random variable parameters, the fixed effects in a linear model. So if we consider these things random, and what happens is if we're using maximum likelihood, and we're going to find out, sure enough, the result we get from the linear model is equivalent to maximum likelihood, although we use least squares to get it. More details forthcoming in future lectures. Then we can think of, as n goes to infinity, that each of these betas ends up having a distribution. And sure enough, if we wanted to take, for instance, if we wanted to come up with the slope, I mean, this is an example that comes from the homework assignment. If we have the effect of experience, and then we have the interaction of the group with experience, this would be a within-group slope of experience right here. If we take 1 of the experience slope and add it to 1 of the interaction. So we know this is a nice weighted sum of random variables. Sure enough, you know each of these terms has a mean, has a standard error, or a variance, right? The variance is the standard error squared, by the way. And what you don't get out of the package right directly in your output, although if you delve into it more, you'll see it in the linear model function, we don't get the covariance between these two effects. We could find it. Multcomp finds it, but we don't get it. So to actually compute, let's imagine what the standard error of this new estimate happens to be. We have to know the covariance, right? It's negative 0.08756. So we know the expected value is 1 times the original value of experience plus 1 times the interaction beta weight. So put those together, we get negative 1.016. What do we do about the variance? The variance is 1 squared times the original variance of beta for experience, 1 plus 1 squared for the original variance of the interaction, plus 2 times 1 times the covariance between the two, which would give us a variance of 0.0653, or the standard error of that new estimate of 0.257. And with that standard error now, we could form a Wald test. We take 0.85, the original, or the new estimate, negative 1.016, and divide it by 2.57, and this, sure enough, is roughly equal to, what, 5 something? That thing should follow a normal distribution as n goes to infinity. So now we have a way to do a test statistic. Okay, so that's the first why I told you that story. The next part is what do we do with the general linear model with what we've learned? Here's our linear model. We have an outcome y. It's continuous. We have a set of predictors. This is what we call the model for the means. We have a residual term, and the residual term follows a normal distribution with a variance of sigma squared e. So what we're going to say is yp is dependent on the linear combination of x, z, and e, and therefore the general linear model provides a conditional distribution of y given x and z. But we're not making any assumptions about x and z. They're constants in this example. And furthermore, each of the regression slopes are constants as well, right here and right here. So that's actually why they're called fixed effects. So if we do some algebra of expectations, if we wanted to figure out what we would say the expected value of y happened to be, in this case it's really the expected value of y given x and z, it's a conditional expectation. We take the constants here, and we know the constants shift the expectation by the constants, so we can pull them out. And we're left with the constants plus the expected value of E. Well, we know by definition the random variable E has a mean of 0. That's an expected value, so it goes away, telling us the mean of Y given X and Z is given by the linear combination of betas plus the predictors that multiply them. That's why we call this the model for the means. It literally is filling in the mean spot of the distribution for Y. Similarly, for the variance of Y, we could do the same type of process. Now we've got a constant plus a random variable. Well, we knew from slides before that the variance of a constant plus a random variable, the constant does not shift the variance. So what we're left with, so all this goes away, and what we're left with here is the variance of E, which is sigma squared E by definition, our residual variance. So now what we're seeing is that the linear model is telling us that the mean of Y depends on where X and Z are. It falls on a line with X and Z, and that for every given value of the mean of Y, we're expecting the variance to be constant or homoscedastic at sigma squared E. Those are how we see the assumptions of the linear model itself, where we get those from. Now, the distribution of Y given X and Z, we can talk about that as well. Same thing with normal. We found the mean, we found the variance. It turns out, what is the distribution? Well, we use the result that linear combinations of random variables that are normally distributed result in variables that are normally distributed too. So because we saw that we have this linear combination that has a constant and something that's normal, what we can say is that the distribution of Y given X and Z is also normal. Hooray. Well, this is why we get the conditional normality of Y assumption. So knowing a little bit about the algebra of expectations can show you what a model is trying to do or trying to describe your data with. Now we can talk about this in context. Let's take Model 5 from the height weight data example that was earlier in this class. And you'll see that here are the fixed effects that I end up receiving. And our sigma E, our estimate of sigma E is the residual standard error right there. So let's plot what this might be. Here's a picture of the GLM with distributions, right? If you have a regression line, here's X and Y. These are just some pictures for it. You have your regression line. The regression line represents, this is the expectation, right? Expectation of Y given X. But the error for it, every error is constant across that line, so you could think about having a normal distribution. So for any given value of X, 4, the mean would fall where the line happens to be, and the standard error, or the variance of it, would happen to come from sigma squared error. It's the same variance regardless of where you are in your distribution. So we could plot that. Let's imagine we had someone who was a female with height of 62. We would expect their weight to be 27.5 based on our model parameters. We know the variance of that comes from our residual standard deviation squared. Similarly, what we can see here is for a person who's a male who's 76 inches tall, their weight would be expected to be 248 with the same variance. Now, you may have seen in previous classes in linear models that perhaps the variance or the variance window might change as a function of where you are, and that's what happens when we actually put in the estimated sample estimates of what we're doing for our analysis. But this is what we're calling the true values, assuming we knew what beta and sigma squared happened to be. And here's the math behind the picture. Sure enough, we can plug in the means in the normal distribution. We can plug in the residual variance, right? So we plug in the numbers, and we create the plot. And if you really wanted to see what that looks like, I have the plot code in R down here. Right down there. You can see this plot right over here. Okay, finally, the last topic of this class. What do we do about normality or univariate normality in R? If we wanted to check whether this is not SAS, that's a previous class. In R, if we wanted to check whether or not the residuals turned out to be normal, we have methods to do so in R and in whatever package, including SAS. The two methods that I typically use, one is called looking at a plot, something called a QQ plot. which is quantile is really what we're talking about. We take quantiles of the thing we want to be normal. We can compare it to quantiles for the theoretically normal distribution with the same mean and variance. And if they line up on a diagonal, we know it should be normally distributed. But if they don't, it's not going to be. There are also hypothesis tests that work. The hypothesis tests are really sensitive to minor deviations from it. The QQ plots are nice, sort of to look at, a quick visual depiction. So again, a QQ plot, this is how you get to do it, but in R we can just actually use the plot function. We take a model and submit it to this function plot. The value on the right over here is a QQ plot. You see that dashed line is where all of the residuals should be if we have a normal distribution. And yeah, we may have a few that are off here or there, right? But overall, that doesn't worry me too much when I see this plot, and this is sort of from experience. If you see a plot, on the other hand, that looks like this is a credit card debt in thousands, which is a very skewed distribution. The line is where the quantiles should line up, and the dots are where the data happen to be, and you'll see this is absolutely not normal. And that's a typical big violation of normality that you'd see. So QQ plots are great in this regard, and R, sure enough, gives it to you automatically if you just plot your model result from the linear model function. And I can switch over to R. You can see this right here. And here are my values. There's the plot that I have in my slides. It also gives you other terms that we're not going to go into in this class. And finally, we could build a hypothesis test. There are a number of those hypothesis tests that are out there. The one that quickly gets used by a lot of people is the Shapiro-Wilk test for normality. And sure enough, if we take our model and put a $sign and the word residual after it, and submit that to the Shapiro-Wilk or Shapiro.test function, it gives us a p-value. Right? This test, the null hypothesis is normal. The data are normal. So if this p-value is low, we reject that null hypothesis, and the data are not normal. This p-value being somewhat large, we would likely say this is the data come from a normal distribution, or at least we don't have enough information to reject this normal distribution. So there we go. That is our lecture on mathematical statistics. It's a little bit out of the ordinary for a class like this, but I want to give you a little bit more background. I don't expect you to understand the math behind it. I don't expect you to do calculus or any of the computations I want. I just want you to have a nice high-level thinking through this, because it does what it ends up doing is it raises the ceiling of what you can do with statistics. I want to have that opportunity for you. Mainly, this may not seem relevant to you, but really it's critically important, because every model that you end up doing in your career ends up having these properties that you can go and quantify using the methods I briefly talked about today. So it's going to help you understand when and when not to use a model, or how to evaluate whether the model is working like you think it would. So that's all for now. Thank you for watching.